Hi everybody. I thought I would go through question 8 on force components. So we did this in class, the last lesson, and I know everyone has finished all of questions from 1 to 7, and I said do 8 if you can. It's not really a hard question, there's just an asterisk around it, and it's to do with running and sprinting. So here's a question. When a sprinter starts a race, the two main factors that affect her running time are the speed at which the race is run and the acceleration from rest up to the speed. Now, A, what physics quantity governs the size of the starting acceleration? So you know when you're learning about forces, when the forces are balanced, acceleration is 0. Now, when there is an unbalanced force, it causes acceleration. So greater the unbalanced force, bigger the acceleration. So the physics quantity that governs acceleration is the force. Now, sprinters create the accelerating force by using their back leg to push down and back against the ground. Assume that the direction of the force applied by the sprinter to the ground is parallel to the direction of the sprinter's lower leg. Now, when the Olympics Games first started, sprinters would take off from a position in which they were standing up but leaning forwards. Okay. Now, if the force developed in the lower leg is 950 newtons and the angle theta is 35 degrees, calculate the horizontal and vertical components of the force. So this is question B from 8. So that's the horizontal. Here's your 950 newtons. The angle is 35 degrees. And we have to calculate the horizontal and vertical components. Now the horizontal component is 950 cos 35 and the vertical component is 950 sine 35. So if I put that into my calculator, what do I get? So I just go 950 cos 35 and I get 778. So the horizontal component is 778 newtons and the vertical component is 950 sine 35 and I get 233 newtons. Okay, so that's question B done for you. Question C, which of these forces is used to accelerate the sprinter? Now you can see two forces. The sprinter is running horizontally. So we need to use the direction in which she is running, in which she is accelerating, and that's the direction of the unbalanced force. So it's going to be the horizontal component of that force. Okay? Now, assuming the sprinter is not able to develop a greater force, how could the accelerating force be increased? So what can we do to make the size of that bigger? What she can do, and she can't change the 950. So what she can do is she could crouch lower down. When she crouches lower down, the vertical component is going to get smaller, but the horizontal component is going to get bigger. When she crouches lower down, what's going to happen to this angle? This angle is going to decrease. Okay, so that's the answer. Now assume a typical force of 110 newtons and a typical angle theta is 20 degrees. So this is a whole new set of, this is question E. So typical force of 110 newtons, because today people are stronger, okay, and they're going to crouch lower. So this is 20 degrees now. It is 35, it's 20. Calculate the horizontal force developed by the sprinter. So the horizontal force is 1100 cos 20. You put that in your calculator. You get 1100 cos 20 and you get 1033 newtons. That's a horizontal force. Calculate the size of the vertical force. Your vertical force is 1100 sine 20, so that's going to be less. 1100 sine 20, and I get 376 newtons. Okay, state what happens to the size of the vertical force as the sprinter crouches lower and lower. So as she gets lower and lower, the size of that force is going to get smaller and smaller. Okay, it's going to decrease. In what way will this affect the sprinter's ability to make a good start? If she crouches too low, what's going to happen is when she's going to push her foot back, she's going to slip. Okay, it's going to, so what they do today is they have starting blocks. When you run a race, there are starting blocks against which you can rest your foot, and that prevents your foot from slipping, and you can crouch quite low and the starting block will prevent your foot from slipping. So that's the answer to question 8, and I hope you can do that in your books. Bye for now.